everyone, welcome to a new video on AI World for You. In this video, let us see about Uninformed Search Strategy BFS. So what is this uninformed search? Uninformed search means it has no domain knowledge or additional information about the goal state. So without knowing about the goal state, it needs to carry out the search as iterations and reach the goal state. That's why we call this as blind search as well. Uninformed means it has no prior information or no domain knowledge regarding the goal state. Under uninformed search strategies, let us discuss about BFS and DFS. In today's lecture, I will cover about BFS. What is BFS? And let us see BFS with an example. So BFS stands for breadth first search. As the name suggests, here the algorithm is going to proceed with the search in a breadth-wise, that is width-wise. So it will search each and every level and then go to the next level. That is all the elements in one level and then go to the next level. That is your BFS. BFS algorithms have a lot of applications and are gaining importance these days. So let us see what is this BFS about. It is one of the most common strategies used for traversing through a tree or a graph. And here, as I said, the algorithm searches breadth-wise. That means it will search each and every node and then go to the next level of successors. So before going to the next level, it will complete all the nodes at a particular level and then go to the next level. So BFS will follow one data structure which is first in, first out. It will follow the queue data structure. So whichever node is visited first, that node has to be dequeued from the queue data structure first. And it will guarantee finding the shortest path because it is going to visit each and every node. It will have information about all the nodes in the tree. So it can provide the shortest path for us. Now let us see one example of BFS. So here I have shown a tree. That is, we have S and we have its successors A and B. And then again A has two successors C and D. B has two successors G and H. And C has two successors E and F. D does not have any successor. And G has one successor node which is I, and then we have K which is the successor of E. So this is what is the example we have taken, how the BFS algorithm can be executed and used here. Let us see that. So as we know, BFS will perform its search breadth-wise. So starting from the first level, level 0, it will first search for all the nodes in level 0. So in the queue, first S is noted. S enters the queue. And then what happens is, now the successors of S should enter the queue. So already S is there in the queue, first in first out data structure. And now we are going to add its successors. Who are the successors of S, A and B? So I am adding A and B in the queue. So this is my element. S is going to be dequeued, right? This is going to be dequeued. And which elements are enqueued in the queue? A and B. So S is getting dequeued and A and B are getting enqueued. I will denote it shortly as E. So in the next step, if we see, S is already dequeued. So next in the list is A. And then we have B. So after this, what we need to do is, we need to enqueue the successors of A because the next in the list is A. So we need to look at the successors of A. Who are the successors of A? C and D. So we need to add C and D in the queue. So I am adding C and D. I am enqueuing these two items. I will denote as E for simplicity. and I am going to DQ A in the next step. I will indicate as D for simplicity. So in the first step, I have started my search with S, which is level 0, which is at level 0. In this particular level, there are no other nodes. So I am going to go and explore the next set of elements in the next level. So in the next level, I have A and B. I have added them in the queue. Next, I need to go to next level. So when I go to the next level, first I will explore the neighbors or the successors of the element which is there in the queue, because this follows first in first out strategy. So here we have A, and A has two successors C and D, so we need to explore them first. Next, after dequeuing A, who is there in the queue? B is there. So now I need to explore the successor nodes of B. And who are the successors of B? G and H. So next in the queue, I will write as this A is being dequeued. So I will write B, C, D, and now I need to write G and H, because G and H are the successors of B. So I need to include them in the queue. Next time I will be dequeuing B, and next in the list is C. So now C has two successors E and F. Therefore in the next step I need to write C, D, G, H, and now I need to include E and F also in the queue. Now what happens is I need to check if this E and F are the only children in the level. So E and F are the successors of C. I have already done that. So after dequeuing C, I need to check for the next element, which is D. But D has no successors. Therefore, I need not go for exploring the successors of D. I need to go to the next element in the queue, which is G. So G has one successor. Therefore, now I need to add I in the queue. Now I have this G, H, E, F and I in the queue, right? So now I need to dequeue G and check if H has any successors. But this H element, it has no successors. Therefore, I am done with all the nodes at that particular level. I need to go to the next element in the queue, which is my E. Now E has one successor, which is K. So I need to include that in my queue. So I will write G, H, E, F, I and K. But already I have dequeued G and H. So I need not mention these two here. It's just E, F, I and K. So each and every node, again I go on exploring. Already E's successor K is added in the queue. So next I will go for F. I'll check whether it has any successor nodes. Next I will go for I. I will check if it has any successors. Next I will go for K. So like that I am going to check each and every element in the queue, and I am going to check if it has any successor nodes. If it has successor nodes, I need to add them in the queue. And as per the order of the queue items, I need to go for the traversal. So here the path to BFS implementation is given. So S, A, B, again B to C, then D, G, H, then E, F, I and K. So this is how we have gone for the implementation, that is level by level. First in level 0 we have seen S, in level 1 A and B, then in level 2 C, D, G and H, in level 3 E, F, I and finally in level 4 we have K. So it will explore all the nodes in each level and then go to the successor nodes of the next level. This is how BFS implementation will be done, and from this now the BFS algorithm can tell us the shortest path. Which is the shortest path to reach the goal node K? The shortest path will be S, A, C, E and K. This will be the shortest path. It need not go for exploring the other nodes to reach K, right? So BFS algorithm will be implemented in this manner it will explore each level breadth-wise, and it will go on searching all the nodes and reach the goal node and then suggest the best and shortest path. Coming to the properties of BFS, we can say that it is complete because it will always find a solution if one exists. And the optimality, if we check the optimality, we can say that BFS is optimal because it will provide the step cost of each and every step, and also it will find the shortest path for us. Coming to the time complexity, since it explores all the nodes level by level, we can say that it takes some time. It consumes a bit of time, and we can denote it as O of B power D, where B is your branching factor, that is the child or the successor per node, and D is the depth of the shallowest solution. Coming to the space complexity, we say that BFS will store all the nodes at the current depth level in memory. So we can call it as memory hungry. It will occupy more space because it will explore each and every node. Space complexity also is indicated as O of B power D. Coming to the advantages and disadvantages of BFS, it will always find the shortest path. That is one of the major advantages. And it is a very simple strategy to use. Nothing complex is there. It will just traverse through the nodes one by one, level by level, and go on implementing. And always it will give us the solution. So BFS will give us the complete solution. And also it works well for grid-based problems as well as puzzle and maze-based problems. Coming to the disadvantages of BFS, we will call it as memory hungry. That is, it will store the information related to all the nodes that it is visiting. And since it needs to visit all the nodes, it will occupy more memory space, and it is not suitable for deep graphs. Coming to the applications of BFS, the main application of BFS is GPS navigation. So if we observe, the GPS navigation tool is able to suggest the shortest route for us. Because it explores all the possible routes, it can tell us which is the shortest and best route to take, right? So GPS navigation is one of the major applications of BFS. Coming to puzzle games, BFS helps us to solve puzzle games like 8 puzzle problems. And in social media, in order to go for finding the mutual friends, first it needs to explore the friends of one particular person. Then it needs to go to the next level and explore that person's friend. So it will go level by level and explore all the friends and suggest that these are the mutual friends. That is also a commonly used application of BFS. And in network routing and AI path finding also, we use BFS. So I hope you understood what is BFS, breadth first search, and how it is getting implemented and how it is able to give us the shortest path. In the next video, I will discuss about DFS. If you like this video, please like and hit the subscribe button, and do share the video with your friends. And don't forget to hit the bell icon for further updates. Thank you for watching.